Good afternoon, everyone, and welcome to today's joint EOL-ACOM seminar. I am Sarah Woods, and on behalf of EOL and ACOM, I'm pleased to introduce Dr. Sara Lance, research faculty at SUNY Albany. Dr. Lance graduated from Arizona State University with a bachelor's degree in chemical engineering in 2002. Since then, Dr. Lance has focused her research efforts on the experimental study of aerosol cloud interactions in Earth's atmosphere. First as a graduate student at Georgia Tech, where she studied the subset of aerosol particles acting as cloud condensation nuclei, then as a postdoc at NOAA and research scientist at a private company, Stratton Park Engineering Company, focused on measurement of cloud microphysics. Dr. Lance is now research faculty at the Atmospheric Sciences Research Center at SUNY Albany, where her recent work focuses on the chemical composition of cloud water and cloud processing impacts on particulate matter. Please join me in welcoming Dr. Lance for her seminar, Whiteface Mountain as a Natural Laboratory to Study Chemical Processing of Aerosols by Clouds. And for those of you online, please feel free to post your questions on Slido at the bottom of the page, and we'll take them during the Q&A. Thanks, Dr. Lance.
Thank you, Sarah Woods. So this is a photograph from the summit of Whiteface Mountain looking down on Lake Placid. And first of all, I'd like to thank my students. One of them is in the audience today and is also featured in this photograph, Archana. So she's starting to do a lot more work up at Whiteface Mountain. And Christopher Lawrence, who's done a lot of the work that's going into the talk today, as well as the Adirondack Lake Survey Corporation, who did a lot of the measurements going back decades, and the Adirondack Watershed Institute. And so this site has a long history. And so I'm going to talk about this long-term record at Whiteface Mountain of the cloud water chemistry, and especially highlighting the work that was in this recently published paper by my student Christopher Lawrence, and the relevance to the atmospheric chemistry and potential driving factors for the observed increasing trend in organic carbon that we see. And so this is what I'm going to focus on, and then the new and ongoing measurements at Whiteface Mountain, which includes cloud water organic acids, aerosol and cloud droplet residual chemical composition, and volatile organic compounds, which we're going to be starting to do with a collaboration here at NCAR with Eric Abel. So to give a little more background, if you're interested in how this work developed, early on when I started at Albany, we had a cloud water chemistry workshop at Whiteface Mountain that was led by myself, Mary Barth, and Anne-Marie Carlton. And we have a summary paper in BAMS in 2017 about that. It was talking about having a coordinated effort, modeling and measurements coming together to try to tackle this really challenging problem of multi-phase chemistry. And then there was a pilot study in 2017 that we titled Chemical Processing of Organics Within Clouds, or CPOC. And I have an overview paper in BAMS from 2020, and there's another paper from 2019 showing the below cloud aerosol composition, which is really predominantly organics. So we've really, I think you could say that Whiteface Mountain is well established as a natural laboratory to study chemical processing of aerosols by clouds. And originally, the site was focused on the problem of acid rain. And so acid rain is, it's not as much of a problem anymore. So just to remind ourselves what that was, is gas phase SO2 emissions from coal-fired power plants. When they reacted in the cloud water, in the presence of sunlight, it produced sulfuric acid. And so this ended up depositing on the ecosystem and causing damage to the plants and the fish in the lakes. So there was a concerted effort to reduce SO2 emissions from coal-fired power plants, which was relatively easy because there are point source emissions, and it was just very few locations. it's not widespread like organics are. And as a result, acid rain was dramatically reduced, as well as air quality was improved due to the reductions in the sulfate aerosol mass. So you could claim this is success, and end of story. We cleaned up the atmosphere. And so you can see this is basically along the entire Northeast US, there's been a really dramatic change in the sulfate aerosol. So that's shown here on the upper. This is shown here with the recent paper from New York City. So bottom line, studying only the aerosol and gas phase chemistry misses important processes. Cloud droplets provide a medium for aqueous chemistry that transforms both particles and gases, and this is well established for sulfate. But the same is also true, and we're learning more about the production of condensed phase organics from the volatile organic compounds. And there's a lot more that needs to be understood about that process. So this is looking at the long-term trend at Whiteface Mountain in terms of the annual means concentrations of the dominant ions, which is the sulfate in red, nitrate in blue, ammonium in orange. And so we have some record from pre-1992 that just select, we don't have like the entire season, but there's some indication that we had higher organic carbon in a long time ago, decades ago. But you can see also on the right axis that the organic carbon, total organic carbon has been increasing since we started routinely measuring it in 2009 in the cloud water at Whiteface Mountain. And so this is a new finding that we put in this paper. And I'll talk a little bit more about that. So yeah, obviously the sulfate is decreased substantially. The nitrate as well, so it's from NOx emissions from vehicles. And ammonium is kind of, it went down a little bit, partly because of the sulfate reductions. So they were kind of tied together through secondary processes early on in the record. And then they started diverging in the later part of the record. And it's sort of flatlined a little bit in terms of ammonia concentrations. And as a reminder, TOC, or total organic carbon, is just the most basic information about the organic molecules. So it's just the carbon backbone. So you can see in this example, everything we eat is organic. And so these are two examples of organic compounds that we are used to in our everyday lives. They're both very similar. They're both organic acids. So they have the same functional groups on the end with the double bond O and the OH, but they're obviously very different. They don't mix together. And they have very different properties. So another thing that came out about the long-term trends that we saw really popping out was the fraction. So on the left axis in black is the percentage of samples that were being classified as invalid. Came up to above 50% in 2020. And so we were concerned. We were basically throwing out half of the data using the criteria that people had been using since the beginning of the record, which was if there were this ion imbalance. So they looked at the relative percent difference, cations and anions that were measured, and if there was a big difference between them, they would just ignore those samples. And so in the past, it was only about 10% of the samples, but now it's about half of them. So we wanted to look more in depth at what these samples were and why this was happening. And so you can see this is the average, or the annual average. Sorry, this might be the median. Yeah, this is the median cation to anion ratio. And so it's been above 25%, imbalanced since, on average, since about 2010. And it's been continuing to grow. And so we actually saw this same type of behavior in some of the rainwater samples. And so that's another reason we don't really think that this is an artifact, which is the reason why they were throwing out the samples or ignoring them in their analysis. So there have been numerous studies that have looked at this data, and they almost all all the ones I've seen have ignored the samples that they call invalid, that were based on this ion balance. So if we look at the ion balance versus TOC, where the ion balance here is on, in terms of just cations, some of the cations minus some of the anions, and TOC on the y-axis. So this is just from 2009 when we started routinely measuring the TOC. You see there's a pretty decent correlation. So from that, we're inferring that a large fraction of the missing anions are organic acids. And we're not the only ones. Other people have come to this conclusion as well, even though they're not measuring the organic acids. They're just surmising that. And in fact, in this study that was published in 2021 from rainwater samples, they inferred this without any TOC measurements. So this is actually the criteria that had been used for a long time for the valid classification. They had two different thresholds. So if the relative percent difference was less than 25%, then it would be considered valid if the concentrations were pretty high, above 100 microequivalents per liter, which is sort of like micromoles per liter. Some people aren't used to using equivalents, but it's the moles per liter times the number of the charge. So sulfate, you multiply the molarity times 2 to get equivalents. So anyway, and then minus 100%, I'm sorry, if the relative percent difference is less than 100%, then it would be considered valid if both the cations and anions are less than 100 microequivalents per liter. So this was looking at just the valid data. So this is very similar to what previous long-term trend studies, I think the previous one came out to 2013. And so we're basically, since we're only including the valid data, this is very similar. I think we looked at the medians instead of the means for this. So there's some slight differences in the way we handled the data, but I think that's sort of just duplicating what had been done before with addition of the last few years. And the other thing I should mention, so you might see there's a TOC and a WSOC here. And so the TOC is the total organic carbon, and WSOC is water-soluble organic carbon. And the water-soluble is what we are measuring actually in the last several years, because we're routinely filtering our samples because we want to better capture the organic carbon and the organic acids. And we're concerned about degradation with microbes. And so we actually looked in closely at the samples where we did both the TOC and WSOC, so with and without filtering, for a subset of these samples to see that this was a good, we had a very good relationship between them. And so anyway, the actual measured values for these last 4 years were these lighter green colors, the WSOC. And then from the ratio between the two for the samples that we did look at, we inferred the TOC. And so that's where the trend is coming from. And so you see an increase, even if you were looking just at WSOC, there's an increasing trend, just the valid samples. If you look at all the samples together, the increasing trend is much higher. So there's a much faster increase, about 2.5 times faster. There were effects also on the sulfate trends, the nitrate and the ammonium. They are actually not decreasing as quickly as they were when we only include the valid samples. So this is comparing the valid and invalid samples directly to each other, and all the different types of analytes. And so you can see the really big difference. So in pink is invalid, and blue is valid samples. So they both have offsets and also different trends over time. I think the thing that stood out to us a lot was that the TOC was so much higher in the ones that were considered invalid. And there's also like a sort of, I mentioned an inflection point. There's, they sort of crossed here in about 2009. So it seems like that's when a lot of things around the middle of, or the end of the 2000s is when things started to really shift in lots of different analytes. Another thing you might notice is that the liquid water content was higher in the valid samples than in the, so this is liquid water content, so how juicy the clouds are. And so that's playing a role in the concentrations, but it would affect all the concentrations equally if it were just diluting. So this is looking more closely at the long-term data set in terms of each individual sample from that period from 1994 to 2017 in this case. So this is looking in terms of the pH of the samples versus the liquid water content that the samples were collected at. And so you see it spans a really big range in pH, so several orders of magnitude in terms of hydrogen ion concentrations. And the behavior on the lower end of the pH is sort of what we expect for dilution. So if you just have water vapor condensing, so the cloud droplets activate, and as the cloud is growing and there's more condensation, the liquid water content increases, and that's basically just diluting what's already there in the cloud droplets. And so that's the type of curve that you would expect for that process with a given starting pH. And so we kind of see that shape with the data set. We also see this kind of shape where the high pH also seems to decrease at the higher liquid water content. And that is less easy for us to explain, and we tried to think of lots of different ways to explain it, but we found a better way of looking at it. So if you look at this in terms of sulfate concentrations, you can see this bimodality. It's very noisy, but there's the lowest concentrations kind of sulfate are around 5.5 or so pH. And then it seems to go at the higher pH, you get higher concentrations of sulfate, which is counterintuitive. So one thing to remember about cloud droplets is that they form on aerosol particles. And so what are aerosol particles? So this is an example, size distribution, actually it's the mass distribution of measured analytes, chemical composition of aerosol as a function of their particle size from Toronto in 2011. And so this is just upwind about a day. And so you see there's a big difference between the supermicron and the submicron particles. There's basically what we think about as the secondary aerosols that are produced from the gas phase, the ammonium, nitrate, and sulfate, which are mostly associated with human activities, or they are also associated with natural activities, but this is where the huge perturbation from humans is really especially strong on this side of on the submicron particles. And then on the large side, we have calcium really standing out. And the calcium, which is often used as a tracer for mineral dust, is contributing a significant fraction of the mass, especially in terms of calcium mass. But it's not found in the majority of the cloud droplets. So you're looking here in terms of a mass scale, so they look like they might be comparable. This might be slightly fewer droplets or something, but it's actually, because it's on a mass scale instead of a number scale, these ones are actually much, much more numerous. So we did the calculations, and these would actually contribute less than 1% of the total number of particles. Since we know their size and their mass, so we can figure out the number from that. So these particles are they're externally mixed. They exist in like separate realities. They don't mingle in the atmosphere, and at least prior to collision coalescence. So for these clouds that we're studying, which are not raining, they actually don't mix together. So we created this adjusted pH, or we actually changed it to estimated cloud droplet pH. So this would be for the vast majority of the cloud droplets, what we think the pH should be. So this is inferred from measured pH, and then also the calcium, and we added magnesium as well, because that had a slight contribution as well. And we think that the magnesium and calcium is not actually in most of the droplets. It's just a very small number of them. So it's important for trying to understand atmospheric processes as the droplets actually exist in the atmosphere. And so that's what we're trying to infer. So if you do that adjusted pH, you get this much simpler relationship. With sulfate, for example, the concentrations really decrease as you approach this 5.6, which would be what we expect the pH for the very cleanest clouds to be in equilibrium with CO2 in the atmosphere. So this makes a big difference, especially in recent years. We can have delta. This is the pH for individual samples. You can see there's a huge span. But for the annual average, you can see the original, just taking the average of the samples, the bulk measured values, you get, it's pretty similar early on, and then over here it's entire pH unit or even more different. And the other thing is that the trend really flatlines since about 2010 instead of continuing to increase. So another thing we saw that really popped out, we were trying to understand this relationship between the organic carbon and the pH and why there might be this sort of inflection point. And that really disappears if you take into account the calcium effect on the pH. And so this, I think, is telling us that the cloud droplets, the vast majority of the cloud droplets are where the vast majority of the organic carbon is. And they are, so this is inferred. It's, so we need to actually do some tests to figure out if this actually makes sense. So this is looking at the same data set all the way out to, this is including the last 4 years. So the ones that are in stars here are actually the water-soluble organic carbon. And so you can see that there's a lot of outliers, especially in 2021. And so we found during this event that there was this smoke happening from the bootleg fire and active fires in the the central Canada, southern Canada, that were impacting us. And so this was an exceptional season. This is water-soluble organic carbon, so it was exceeding the total organic carbon for the past 10 years. And so this is the filter. I told you we were filtering the samples. It was black, and the visibility was very low. We had black carbon measurements. We could see very clearly this was associated with the fire. And this paper came out not too long after and showed that the event was really widespread over New York State. And there were actually 2 episodes of it. So we know that there's an influence from smoke on this organic carbon. And another recently published paper is connecting the higher TOC in specifically Whiteface Mountain cloud water samples with a greater probability of smoke influence. And they used high split back trajectories and smoke products to infer this. The smoke probability they classified as low, moderate, or high, and then they looked at that over this past from 2010 to 2017. So there was not really a readily apparent trend in the wildfire smoke influence. But one thing to note, as I mentioned, is valid data were only included in this analysis. So we want to go back, because we know that that the TOC was much higher in the invalid data and if those are the ones that are most smoke influenced, we're potentially missing the most important data set in this analysis. So we want to work with these co-authors, or this is Carrie Pratt's group, and we want to work with them and see if there's a difference when you include the invalid data. Okay, so if there's an increase, if this increasing TOC at Whiteface Mountain is due to wildfire smoke, which there obviously is some connection, we would expect to see that in the aerosol as well, the aerosol organic carbon. So I've looked at that. This is measurements at 2 different sites. So we have a summit site right at the top, obviously, and then at the lodge, which is often just below, or quite a bit below cloud base, so at the base of the mountain. So we looked at ozone, and we looked at a couple other tracers to see if there was a connection between the 2 sites, and on average, that seems to be true. So that it's a well-mixed boundary layer, especially in the summertime. And so since we're only doing summertime cloud water measurements, you don't see the variability in the composition. But in the aerosol, we have those year-round at the base. So they're conducted at different sites, but we think that they should be related to each other. And so we can see, if you just look at the summertime only aerosol concentrations in red, there is an increase in the slope of about 0.5 micrograms carbon per meter cubed per decade. And whereas the cloud water is about 3 times higher slope, but there does seem to be some increase, but they're not exactly at the same site, and it's very noisy. As you can see, there's a lot of variability. And so we obviously wanted to understand this a lot better and to get, we're not gonna make any strong conclusions just based on this. But if you look at those 2 data sets directly, comparing them to each other on a monthly average basis, for that time period, you can see that there's an offset between them, and there's always more organic carbon in terms of micrograms carbon per meter cubed than there is in terms of aerosol carbon. And offset's about a microgram per meter cubed, but there is some variability, and the highest excursions from that offset are mostly in June and July. And we also looked at the seasonality of the trend in the organic carbon in the cloud water. And so this was in response to one of our reviewers, actually. And it was a really good suggestion. So this has you can see that the increasing trend is every month that we're measuring. But it's especially strong in June. And that even though there's more carbon in July, there's still an increasing trend as well in July. But however we look at it, we see this increasing trend, but it's not as strong in the aerosol. So we're thinking that there's more to it than just the wildfire smoke. So the possible reasons for the trend are that there's other biogenic VOC emissions have been changing, or that anthropogenic emissions, for instance, the volatile organic compounds or oxidants are changing, or greater partitioning of VOCs to the aqueous phase because of changing chemical regime that we've been talking about. So one thing is that the organics are complex and not well understood, and the organics in the aqueous phase have even fewer measurements than the aerosol phase. And so we really have a lot to figure out. And we don't know if this increasing trend in TOC is going to continue. There doesn't seem to be any signs of it slowing down. And we don't know what effect that would have on the aerosol as well. So the other thing that we found was that the ammonium was greater than sulfate plus nitrate combined for a growing number of samples. So at a similar time period, we start seeing this change in the so they're getting more neutralized, basically. But there's more ammonium, so it's beyond neutralized. And so we think that those could be connected, and it could be a coincidence, but it could also be connected to the increase in the TOC. And two potential pathways that we've identified are this excess ammonium is increasing the partitioning of the organic acids from the gas phase to the aqueous phase, or that excess ammonium is increasing the production of organonitrogen species in the aqueous phase. And there's a lot of literature that seems to be kind of heading this direction. This recent paper, I think, really shows it. This is in China, but they were showing the same kind of processes happening, where you had the ammonia, the gas phase ammonia, contributing to these organonitrogen species, as well as the increased partitioning of carboxylates to the cloud water. And so it could be both. And so there's probably a lot of things happening at the same time. Sorry. I was just looking at the time and getting confused. Okay. So obviously the partitioning of the gases matters. So if these volatile organic gases come into the cloud water, but then they evaporate again when the cloud droplet evaporates, then it's not affecting the aerosol mass. So this is one thing that my colleague, Chris Hennigan's group, has been looking at with cloud water samples at Whiteface Mountain. And so they take these bulk cloud water samples back to the lab and aerosolize them and dry them out by just diffusion, and then compare the aerosol organic carbon, the water-soluble organic carbon from the dry aerosol divided by the water-soluble organic carbon from the cloud water. And they found that the ratio of those two for these small subset of these samples was pretty high. So that means there's not much, almost all the gas, this implies that almost all the gases that dissolved in the water stayed there when the cloud droplet evaporated. And so I'm using this term VWSOC to be the difference between these two, the cloud water and the dry aerosol. So that's the fraction that volatilizes off again. But when we looked at that data set from 2009 to 2000, I think this was 20. I can't remember exactly. I think it was up to 2020. We saw there was a lot more variability. Oh, it says it on there. So this is comparing the aerosol and the cloud water ratio. So this is actual ambient data. And so we're seeing that the volatile water-soluble organic carbon can comprise up to 70% of the cloud water. So there seems to be a mismatch. It could be just that we didn't get a good sample that was well representative of this data set, but it's over the same time period. So we're going to be doing more of these to see if we see this variability that we are inferring from the ambient data. But in addition to that, so the method that they used was using the bulk cloud water samples. And so there are potential pitfalls from this method. So this spray from the bulk sample has an internally mixed composition from all the aerosol particles that made up those cloud droplets. So you have the calcium, the magnesium, and all the other secondary species all intermingled, like we talked about before. So then once you reduce the relative humidity, you lose your volatile water-soluble organic compounds, and your aerosol particles then go into the pills for TOC analysis in that method. So what we want to do to be more careful, I guess, is sample the droplets in situ while reducing the relative humidity. So that would mean keeping them separate. So if you have these cloud droplets that have the calcium and magnesium containing droplets, which have a high pH, they're separate. They're kept separate from the ones that were secondarily produced with the low pH. And then you reduce the humidity and keep them externally mixed, and then you can internally mix them after the pills. But crucially, that's after the volatile water-soluble organic compounds have been lost. So we hypothesize that the organic acids are more likely to volatilize when not mixed with these calcium-containing droplets. So we expect to see greater volatile water-soluble organic compounds, carbon, with this method. So we can compare the methods directly. And we have 2 ways of determining this with our new data set that we're starting to collect now. So we compare the cloud water WSOC and the cloud-free aerosol WSOC. So the drawback from this method is that we can't do these measurements at the same time and location because one's in cloud-free air and one's in cloud. So we'd have to look at the before and after the cloud had passed. So the other method is looking at the cloud water WSOC and the cloud droplet residual WSOC. And obviously we can do that at the same time and location, so that's the advantage of that method, but it's substantially more difficult to do. And the advantages of both methods, as I said before, is that we don't have that intermediate bulk sample, which is artificially mixing the calcium-containing droplets, which have a big impact on the pH and likely change the partitioning of the gases. So this is what the instruments look like at this, and this is our building at the summit of Whiteface Mountain. So we have this inlet that funnels the aerosols down into the building where we have the pills set up inside. And the cloud droplet residuals are the particles that are left behind after the cloud droplets evaporate, while the interstitial particles are rejected. And then we can compare the cloud droplet residuals directly to the cloud water sampled from the same cloud to infer the VWSOC. The downstream pills measurements are also directly comparable to the cloud water measurements, so we can get the same suite of analytes from the inorganic ions to the TOC. And so these are some initial results from 2021. So we set this all up for the first time. And as you could see in this previous slide, there's a lot of equipment. And this is very heavy. It's at the top of a mountain. So it took all summer to get it up there. And then the last week of the project is when we finally got some data where almost everything was working at the same time. I say almost. Almost everything was working at the same time. I think on this day, everything was. Most everything was. So I highlight this day. But obviously we're going to need to look at a lot more samples to draw any actual conclusions. But this is showing what the data set looks like. So we're kind of going in and out of cloud here. This is a cloud-free period. That's why the liquid water content's low. And then the liquid water content goes up, and visibility, there's a visibility sensor that goes with the GCVI, also responds. And so from this period on, we're in cloud. And so these are the cloud water chemical composition at 12-hourly intervals. That's the time period that we have for the cloud water. And this is truncated here. But anyway, so the cloud water was sampled here, and you can see the organics were higher than sulfate early on, but then they were even higher, much higher later in the cloud for some reason. So that's very interesting to us. And then the pills, this is the kind of pink color is the sulfate from the GCVI, or from the pills, which is a particle into liquid sampler. And so we were looking at here, this would be the mostly clear air period, and then this is in cloud. So these are cloud droplet residual sulfate concentrations. So you can see there's a discrepancy between them that we have to figure out because they should actually be the same. And so we're probably, to start with, we're going to be looking at the ratios of these things because there's a lot of sampling efficiency things to consider. And it's really challenging to make this quantitative in terms of concentrations. But the ratios are a really, really robust way of looking at it, and that's what a lot of other people have done. And so we're also looking at the total aerosol concentrations. You can see they were up to about 4,000 per centimeter cubed early on in this before the cloud penetration or the main cloud. And then we're also kind of going in and out of the GCVI. So that these time periods that are in white, we were out of the GCVI, so we can compare between the two inlets, the PM10 inlet and the GCVI, and see how things are matching up with the inlets. So it's really helpful for understanding our inlet transmission efficiencies. But obviously, these are only just a few of the analytes. I'm just showing a couple here to try to make it easy to understand. And we didn't actually have TOC in the pill samples for these because we didn't, at that time, figure out that we needed to, we need to collect a lot more volume, basically, to be able to do all these analyses. So now we're operating at 6-hourly intervals to compare with the 12-hourly cloud water samples. So for 2022, we did a lot better. Still not perfect, but we're getting there. And so we collected 300 pills, greater than 300 pill samples, and we're starting to conduct the chemical analysis on these. But we're planning to continue doing these measurements in 2023 and 2024, and potentially also 2025. So we want to develop a really big data set from this and draw more robust conclusions. So this is a summary of what I've shown. So this is come to the end of my talk. So so we're showed like an emergence of a new chemical regime characterized obviously by reduced sulfates by design, increasing abundance of organic carbon, which is for unknown reasons. And so this is absolute abundance, not relative. And the increasing abundance of missing anions, which we infer to be organic acids, and a growing surplus of ammonium relative to sulfate and nitrate. And we also see that there's obviously some connection with the wildfire smoke and TOC, but the increasing trend could also be influenced by heterogeneous chemistry that's happening in the cloud droplets. And new and ongoing measurements focus on the organics and their chemical evolution as they cycle through clouds with goals of obtaining robust statistics on the partitioning, mixing state, and aqueous chemical processing of organic and inorganic chemical constituents. So I want to thank all the funders for this, NSF in particular for the career grant, NYSERDA for supporting, this is the New York State Energy Research and Development Authority, for supporting the cloud water collection and analysis that they've done for many years, as well as NCAR for supporting my students that come out. Chris has come out for, he's been on a ACOM travel grant, which was cut short due to COVID, and also came out for a graduate visitor program fellowship, which was really useful for him to do some modeling work with Mary Barth. And Archana is just starting her Ralph Cicerone fellowship here to do the VOC measurements. And I'd like to take questions.
Thanks, Dr. Lance, for that interesting seminar. If you're online, don't forget you can answer your question or put your questions in on Slido at the bottom of the page. Does anyone in the room have questions?
That was a super interesting talk, Sarah.
Excellent.
I was just, I'm thinking about when you get to more speciated analyses of some things, and you're working towards that, I guess, right?
Yeah.
You think you'll be able to sort of like figure out whether it's fire, exactly, is it fire versus some other contribution to the TOC?
Yeah, I think that we'll have to, that's the goal, is to quantify. I think there's definitely an influence from fire. I mean, it's no doubt, but how much? Okay. And that's the goal, is to figure out. Like I said, we're just looking at organic carbon right now, but the organic acids we're starting to measure those. We've done the measurements out through 2022, actually. So we just need to analyze all that data and put it in the context of all the other data. And then we've done some like high-res TOF AMS on the 2018 samples, which I didn't talk about. But yeah, the resuspension of the bulk samples, we're a little concerned about how that affects the results. So we definitely want to focus on the in situ measurements at the summit, and we definitely want to work with others as well. So we're trying to make it easier to bring in visitors to do measurements there as well. I mean, bringing an AMS up there would be really challenging because it's got a spiral staircase and it's really tight. There's not a lot of power, so we're trying to make it easier to bring those types of instruments in, which we're going to need, I think.
Thanks. I was interested in the challenges associated with getting those instruments up there, so that gives me a little idea.
Yeah. There's a hatch to the top floor, which is too small to fit the instrument. We had to take it all apart. It came all packaged and nice, and we had to take it all apart. It's 600 pounds of equipment just for that one rack, and then hefted up this ladder and then put it back together. So that's why the first year we don't have much data.
We have an online question from Adriana. She says, "Hi Sarah, thanks for sharing this exciting work. I'm curious how your trends might compare to other sites like Mount Washington, which has also been collecting cloud water for many years. Are these increasing TOC and NH4 trends regional? And do you have thoughts on whether those changes are linked?"
Yeah, so I'm not that familiar. I've actually visited them, and they told me they didn't have, the people I talked to there didn't have a lot of data from Cloudwater. They've kind of been sporadic about it and not, so it's harder to know how representative the samples are if it's just a few, every few years or something like that. But we are looking at whether this is more regional. There are the rainwater in particular, there's other, the networks like the NADP. They don't look at TOC mostly, but there's a couple of sites that my student has been looking at. And it does seem to be increasing at those two other sites. I can't remember, Sleepy Rivers, and I forget what the other one was called. So I think it was New Hampshire and Vermont or something. So we think there probably is a regional, and the other thing was that rainwater paper that I cited earlier about the cation to anion imbalance in the rainwater. That was a regional as well. They looked at a lot of different sites, and they found this increasing difference between the two across the eastern US and in Canada. And so that actually came out after our paper was in review. So it was really encouraging, I guess, that we were on the right track for that. And they also, like I said, came to the same conclusion that that was due to the organic acids increasing. The connection between ammonium and TOC, I think, is really interesting. And I really think there's something there, but we really just don't have we just have correlations right now. We can't really prove any kind of causation yet, but that's the goal as well, to try to understand the reason for the connection or the correlations that we're seeing.
Great. Any other questions in the room?
Hi, thanks, Sarah. I'm wondering how labor intensive this all is, how much of your sample collection and analysis is automated, how much you actually have to be there.
Yeah, I didn't really talk about it too much, did I? The actual cloud water collection is fairly automated now. It's a really nice system that was set up before I got there. So I really inherited this really fabulous thing. I mean, it still takes a lot of work to get it going and to keep it going, but it actually, so it has this collector that pops up when it senses there's a cloud there. It's considered passive in the sense that there's no pump blowing the air or pulling the air across. Just there's always wind up there, so there's plenty. But it's active in the sense that it does sense the cloud and then pops up out of this protective housing, and then collects the water on these strings and lets it accumulate, in which we get up to a liter of cloud water from this, or even more actually, that we could take advantage of. But then when the clouds pass, it closes again, and it like has this mechanism for cleaning itself. So it has spray and all these valves to like divert the spray water to the drain. And so we talk about that a lot in the paper about the long-term trends paper, because we had to talk about how things changed over or evolved over the years since the 1990s. But it hasn't changed too much. It's, you know, the important things are there, but they automated it a lot more. So that helps a lot. And then we do have a site operator who's there all the time, so we don't have to drive 2 hours, 2.5 hours up there all the time to like collect the samples or whatever. So he works up there at the mountain routinely, so that helps a lot as well.
So on that note, you mentioned most of your measurements are in the summer. Do you have easy capability to extend those to like spring and summer or spring and fall?
So cloud water would be difficult. I know at Storm Peak Lab they've done wintertime like rime ice. So that's the reason we only operate when it's above freezing because it sticks, and then it won't flow, and then it backs up and makes it really challenging, and it breaks things. But people do it. So they just basically have like a tennis racket kind of thing that they put out there for a certain amount of time, not very long, because you get a lot of rime ice at the mountain sites. And put it perpendicular to the wind and let it blow through there. And it's a lot of manual. That one's very manual. They take it down and you like break the ice off into a bucket and melt it and do the analysis. So that's the thing is I don't know anyone who's figured out how to do that in an automated way. So it's very manual and intensive. And I think the chemical processes are probably different. It's probably very distinct. I'm sure it'd be very interesting, but we were having enough challenges with what we've got right now with this warm phase. So we haven't even started thinking about doing that yet.
Sure, that makes sense. So we have another online question from Mary Barth. She says, nice seminar. I was intrigued by the TOC versus pH plot that showed a more monotonic relationship, yet there seemed to be more nonlinearity at the low pH, and that nonlinearity increases with more recent years. Do you agree? And if so, any idea of what that trend is happening?
Higher TOC at low pH in 2016. Yeah, I mean, that's a great question. It'll take me a minute to get back to it. But I think, yeah, this one has more of the data. Yeah, it's definitely nonlinear. And that's actually the case. Well, it's actually, so pH is log. So it's, if we put it on hydrogen ion concentrations versus TOC, I think it's a lot more linear. But I think I see what you're saying about the change in years. I mean, obviously these outliers seem like they're pushing the trend over more. I don't know. I think the way I'm thinking about these is that they have a lot of primary organics in them, probably, because they're relatively close. At least some of the fires were relatively close, even though back trajectory analysis said it takes like 5 days to get to us because it's kind of swirling around. I'm just guessing that there's a lot more primary plus secondary in these, and so that's why it's sort of like a boost in terms of organic carbon in the smoke plume. Because I think there does seem to be a connection with the secondary, the organics, the nitrate, the ammonium, and the sulfate all really are well correlated with the pH. And so I feel like that kind of implies that most of the organic is secondary, which I think other people have seen as well. If you look at like the AMS, some of the AMS papers, aerosol mass spec papers show that I think that most of the organics are, especially at this site, it's very far from sources, very remote. So I think most of the organics are secondary for this data set, whereas the more recent ones from these fire plumes are secondary plus primary.
Thanks. Any other in-person questions? All right, then I have one. If you go to one of your last plots with the GCVI, your preliminary observations.
Yeah.
So you pointed that the Cloudwater SWOC was like higher later in cloud. Do you have any guesses at what might have caused that?
Well, I mean, not really. I mean, it could be like all of the hypotheses really hold, like that there's more partitioning over. I mean, the exciting thing is it could be some chemical processing. I mean, that's the thing we're trying to understand with a lot of the modeling work is, and that's the other thing I should have said is we're doing modeling work in conjunction with this. So my student Chris and Mary Barth are really, trying to push this forward, and they're focusing on the organic acids because we have measurements to constrain it. But so it's really a big problem. There's a lot of possibilities, I think.
Sure, that's fair. Just curious.
It's under constrained, I would say, at the moment, still.
Cool. Well, if there's no further questions, let's thank Sarah for that exciting seminar on whiteface.
Thank you.